Yeah, let's let's discuss the case of the symmetrical optimum. That is number 3, pi with symmetrical optimum. Before we apply this in our project number 4, I want to explain the theory with a simple IT1 process. Then it's a little bit more simple. IT1 process. And what is an IT1 process? That is just integrator together with one PT1. This is an IT3 process. So I just discuss an I with a PT1 together with a PI controller, except the three other blocks. So we have the following situation: PI with an unknown KC and an unknown TN with an IT1. IT1 is just one block. We could of course express IT1 with an I plus an PT1, but an IT1 is so far also okay. It's a process K, and there is a T1 as the time constant of the PT1, negative feedback, and we discuss the situation in the open loop Bode plot. For this we need the Bode plot of the PI and the Bode plot of the IT1, and the ratio between Tn and T1. If Tn is equal to T1, we have an unstable loop. So we have only the chance if in this phase calculation we have an arctangent which goes more in the positive direction before another arctangent, this one, goes in the negative direction. So at least we have to say that we can only have a stable loop if Tn is larger than T1. We talk about corner frequencies, so the corner frequency of the controller is 1 over Tn, we use it, and the corner frequency of the process is the inverse of the time constant of the process. Okay, then let's draw now the phase curve. All things can be explained with the phase curve. The magnitude curve is not so interesting. Phase of open loop. Phase is completely negative, so we can draw our logarithmic axis of omega, the top region here. We need 2 marks. One mark is at minus 180 degrees, and in the middle we have a second mark that is minus 19 degrees. Then we need here a mark that should be the mark of omega n, and we have here a second mark, vertical mark. This should be omega 1. So this is a, if Tn is larger than T1, then omega n is smaller than omega 1. That should be clear. Okay, we need now the Bode plot of the PI controller. Just I take it as a picture here. The copy from workbook page 16, the equivalent row of the PI controller gives this phase curve. I do this in red and say I mark the PI controller in red. This starts at minus 90 and goes up to 0, and the middle point here, minus 45 degree point, is the corner frequency of omega n. So this starts here, and then this goes up and ends up in the 0 degree phase version. Okay, this is a PI phase, so we can say phi PI, and I do this now for the IT1, and then I add the curves. Now look, I have changed to IT1. the phase of the IT1 starts with minus 90. I do this now in green, starts with minus 90, and then with the middle point at the corner frequency of the process, it goes down to minus 180. This is the process. So we can see the phase starting value, the sum. So I note here this is a green one, and the sum I will do in blue. So the sum of both will end up here. 2 times minus 90 is minus 180. For large frequencies, we have 0 here for the controller and minus 180 for the process. So we have minus 180 for the sum. And if this goes up before this goes down, we have a region where this phase curve is more positive than minus 180. And caused by symmetrical reasons, we can say the maximum is exactly in the middle between both frequencies. So, and the curve has a special symmetry, and because of the arctangent curves here have the same shape, this curve must be a symmetrical curve, and the maximum here can be found exactly at this position. We can say this is phi max. I delete this, don't need it anymore. And the frequency here in the middle we can call omega max. And now we can note some fundamental behaviors. First, we can note some phi max values, and you know that the phi max value depends on what? Depends on the distance of these both points. The farther they have a distance, the larger omega sub 1 is compared with omega n, the more the red curve goes up before the green curve goes down. So the max value is dependent on the difference of both frequencies. We have a logarithmic axis, and the difference of two logarithmic values is the ratio of the frequencies. So phi max is very clear the ratio of the two frequencies, and this ratio is expressed with the value omega n divided by omega 1. If the ratio is 1, we have of course no maximum. If the ratio has different values, we can note these different frequencies. There is a table, I just copy this table from the student paper. So it could be calculated that if we have a phi max value of 30 degree, we need a ratio of 0.333. So that's a factor of 3. The inverse is a factor of 3. With 40 degree maximum, we need 0.198. You see, this is a factor of 5. With 50, we come to 0.132, factor of 6. And the 60 degree value delivers a ratio of 0.0718. Okay, that's the first thing. It could be calculated. There's the sum of two arctangent functions has a maximum depending on the ratio of the corner frequencies. This is just a mathematical knowledge. Another information is omega max is the, I have told you, is the middle value between omega 1 and omega n, caused by symmetrical reasons. Okay, normally the average value, not middle, but average value of two numbers is a sum divided by 2. But now we have to add two logarithmic values and divide by 2. If we want to have the frequency values, then we can say, okay, the sum is a product and the division by 2 of a logarithmic value is the square root function. So omega max is the square root of the product of omega n and omega 1. That is the geometrical average. Maybe you have heard it. Geometrical average. Not the arithmetical average. The arithmetical average of two logarithmic values is the geometrical average of the frequencies. Okay, so we can calculate omega max and we can calculate, caused by the ratio, the phi max value. And now, please look what happens if you have an optimal design of a closed loop system. Of course, we want to have, what is the goal? Large omega d values that cause fast systems, and the phase margin is the distance of the open loop, and the blue is the open loop of our simple system here. The distance of the open loop phase to minus 180 is the phase margin, so phi max is nothing else as the phase margin if my omega d is exactly at this position. Omega d value can be selected 3D by selecting the open loop gain, the cross point of 0 dB line. So we have a free selection of omega d, could be any value, but you see if omega d is small, then we have small phase margin, so bad damping and bad speed. If omega d is large, we have high speed but slow damping, and you can imagine that an optimal point is exactly in this maximum. If in the optimal design we can find out that omega d is omega max, then we can say phase margin is my phi max value. And exactly that is what we call symmetrical optimum. Symmetrical because the curve here, the phase curve has a special symmetry, and optimum as we try to reach omega d within this maximum. The question is, how can we do this? That comes now. This optimal design is the best damping with optimal maximum speed. A good compromise. Best damping with high speed. The phi max value is the damping value, the damping indicator, and the crossover frequency is the speed indicator, and there is no better compromise possible. So the first idea in this design method is very simple. Look in this table. If, for example, you want to have a phase margin of phi max value of 40, for example, then make the ratio between omega n and omega 1 to this 0.198. Yes, 30 gives this ratio, 60 this ratio. So if you know omega 1, here you can calculate omega n, and with omega n, the time constant of the controller. That is the first simple way to come to a result of a design. But there is a better one, because here you have to know this time constant. Maybe there is a way where this time constant of the process is not necessary to know, and that I want to show you in the next step, because here also omega d is missing in this table. You should know, if I know the ratio of omega 1 to omega n or omega n to omega 1, then I know that the ratio of omega max to omega 1 or omega n to omega max is in the logarithmic distances half of this way. In frequencies, the division by a logarithmic value by 2, half of the way, is the square root function. So we can add here a new table, a column, and we can say, okay, the omega n ratio to omega d, omega n ratio to omega d is, the omega n to omega d is half of the distance omega n to omega 1 in the logarithmic values. So this is square root omega n divided by omega 1. So we can extend this table. The square root function of this gives this value. Square root of 0.33 gives 0.577. I look just at the table of the student. The square root of 0.198 is 0.445. This is 0.364, and this is 0.268. The question is, okay, what is this for a help? Why I do this? Because now I know the distance from here, omega d, to this point. So this distance now is given with this number. We know this curve, and this leads to the very simple fact, this angle is known as minus 45. With this distance, if this distance is given, I can calculate this angle. This angle is this part drawn in red. This distance is phi controller, phi pi at omega d, and maybe you can remember this angle we have discussed in project 3. This is responsible for the speed decrease of a PI controller, and this is given in this table. We only need now this phi pi value at omega d, and there is a clear relation between this value and this is here, of course, minus 45. That's the value if both frequencies at the same time, but we don't need this value. Wipe it out. We need the value of a 30-degree phase margin. Then the calculation of this value gives this number. This is negative 24. I show you just in a few seconds a way to calculate this. Just fill in now the results. The phase margin is the controller phase as omega d. Phi pi at omega d can be calculated as minus 90. It's the phase equation of the PI controller, well known, we have used this several times. Arctangent omega d times Tn. This is minus 90 degree plus arctangent omega d, and Tn is just Tn, note here, Tn is the inverse of omega n. So this is omega d divided by omega n. And omega d divided by omega n is the inverse of this number. For example, if omega d divided by omega n is 1 divided by 0.577, and I put this number here, I get phi pi is minus 90 plus arc tangent 1 divided by 0.577, and if I calculate this with my calculator, I get minus 29.98. So this is very good, minus 30 degree, this value in my table. And this can be done for any other of these numbers. Can just convert this into the phase value at omega d of the controller, and this is exactly that value we need to design a PI controller with symmetrical optimum. Yeah, because this is the PI controller value at omega d. This is the phase margin at omega d. Yeah, no, this is phase margin. Controller phase is omega d, and so with this both values, phi c at omega d, with these values you can easily, place is now small, and calculate the process phase at omega d. Here this is minus 105. This is minus 110. This is minus 160. And this is minus 120. And so you need just the cross point of the process phase with this value, which leads to omega d, and then your controller is designed. If you have omega d, omega n can be calculated with this value, and Kc with the well-known magnitude equation of Nyquist, and then the controller is well designed. So what you have to learn is, in the symmetrical optimum, the desired phase margin, what you want to have, automatically leads to the optimal phase of my PI controller. So use this table to get the PI controller values. If you have intermediate phase margin values, so for example, if you want to have 55 degree phase margin, then you have to interpolate between these both values. So this will be 17.5. Yeah, so I think that is not really a big problem to have intermediate values using this table. Okay, this is the theory. PI with symmetrical optimum, theory with IT1 process. And what is the experience with this table? This also gives good design results if you have not only IT1, for IT1 this is exactly true, or you have an IT2, IT3, IT4, or an I with any number of PT1s, then this table gives optimal design for a PI controller if the process has an integrator. In our 3PT1 plus I process, now we can go this way. Phase margin should be 60 degree. That, yeah, use table, leads to phi pi at omega d is minus 105 degrees, and this leads to omega d value in my Bode plot. For I look here, I think the workbook now has to be shifted into this window. I have to go to page 42, I think. Yes, 42, that's a P controller, and PI with pole conversation. No, that's too far. Nee, das ist alles nicht richtig. So, sorry for this. P controller. Yeah, the P controller needs a value here of minus 120 with the phase curve, Now the PI controller with symmetrical optimum looks the same diagram, the same phase curve, same magnitude curve. Now we look at -105. Going to the cross point gives, of course, a smaller omega d values. The resulting value here is omega d is 1.55, they rounded to 1.6. Omega d is 1.6 per second. See workbook page. What was this for a page? It was page 43. 43. And we read, of course, we need this advance the magnitude value of the process at this position gives here it's the same at omega d 1.6. Go up to the blue magnitude curve, and the cross point here is negative, not bad. With 4 divisions here. 4 division means 10 degrees, 4 division, 2.5 degree distance. So this is negative 75. Negative 75. Look here, where is omega d? Yeah, the process magnitude negative 79. Okay, with my reading, this will be negative 18. Negative 18 dB, which is equivalent to is 0.126. And with this Kc in the normal way, Kc is now, calculate this with the magnitude equation of Nyquist. We have done this now several times, so I can skip this way. This gives in my workbook, I have calculated Kc is 7.6. Kc is 7.6. Let's compare this now with our P controller design. Then omega d, speed indicator 1.6. The P controller, where is it? The P controller has an omega d of 3.2. The PI with a symmetrical optimum 1.6. That's just factor of 2. You are a factor of 2 slower, yeah, caused by the integrator of your controller. And this is exactly that what happens if you must use an integrator in the controller. The result is you are very slow. Okay, I close this with the hint that in the next video you will see the simulation of this project number 4. This will be video number 59.